Hello, guys. Welcome to today's segment of Econometrics, and we're going to look at the Toda and Yamamoto causality test using Eviews. And before we do that, we're going to do a recap of the previous causality test we considered, and that is the gradual causality. We discovered that gradual causality examines whether the past values of one time series can improve the prediction of another time series after controlling for the past values of y itself. We also discovered that the gradual causality essentially looks for a predictive relationship where the cause independent variable precedes the effect dependent variable in time. And very good criteria for considering gradual causality is that the data must be stationary, either by differencing or by the trending, and two, one must choose an appropriate lag length before you can determine causality relationship. And that was why important questions that were asked was, what if data are not stationary at first difference? Can causality relationship still exist between the variables? Two very important questions. And what is the answer? Yes. Causality relationship can exist between variables that are non-stationary. Why do we say that? A procedure introduced by Toda and Yamamoto in an article titled Statistical Inference in Vector Autoregressions with Possibly Integrated Processes, published in 1995 by the Journal of Econometrics, volume 66, pages 225 to 250. Now, Toda and Yamamoto causality test builds on the gradual causality framework. That is, the causality test assesses whether one time series can help predict another time series. And two very important things about the Toda and Yamamoto causality test is that it is designed for time series data that are non-stationary at their levels. Please note, it is designed for time series data that are not stationary at their levels. And then there is no need for pretesting for co-integration. That is it. Okay, so now we'll have to go to the basic steps with Eviews. And please, you have to follow carefully so as to know the procedures. And we have a linear regression model. GDP is a function of money supply. And the step one is test each of the time series to determine their order of integration. The first thing we do is to go to our Eviews work file. Here we have the GDP and the money supply. The first is to test the order of integration, check their level of stationarity. Okay, we go for GDP, check for GDP. We use the standard unit root test, use ADF. Okay, at level GDP is probability value is 0.9883. Now check for the first difference. First difference for GDP. Yes, at first difference we have probability value of 0.0175. So GDP is stationary at first difference. So that is that. So we also have to check for money supply. Okay, we close out of GDP. Okay, money supply. Okay, we now big view, and then a standard unit root test. Then we click on level. We check. Okay, money supply is not stationary at first difference. At level, and at first difference it is also not stationary, 0.9942. Okay, and let's see the second difference. The second difference is also not stationary, so at the ADF framework is not stationary. Let us look at money supply using the Filiperon framework. And Filiperon, we go to level. Okay, at level money supply is not stationary. Okay, let's check at first difference in the Filiperon framework. Okay, at first difference, money supply is not stationary because the probability is greater than 0.05. Okay, let's also say second difference. Okay, second difference, money supply is stationary at second difference at the Philippean framework. Okay, let us check that of GDP also at the Philippean framework. Though we have determined that using the ADF, let's check the Philippean. Okay, so that unit root at level, okay, 0.9975. Okay, now check first difference. Okay, yes, at first difference is actually significant. Okay, now so what do we see now? Let's look at the expanded view of it. The result is that at first difference, GDP is stationary, while money supply second difference stationary. But now our main concern is that the Toda-Yamamoto uses the variables that are not stationary at their level. So we are interested at their stationarity at their level. So at their levels, GDP and money supply are not stationary. Okay, we'll now move to the next step. The next step is what? Determine the maximum order of integration. So we'll go back to that table and we'll look at it. The table, the maximum order of integration is what? The highest is what? I2. So the maximum order of integration is 2. If our variables were stationary at levels and then the other one at first difference, then the maximum order of integration will be 1. For this one, the highest is what? 2. So our maximum order of integration is 2. Okay, so now move to the next step. Next step is specify a VAR model in the levels of the data, regardless of their orders of integration. Okay, we'll now go to our Eviews work file, specify a VAR model, so it's a VAR. Okay, we click on GDP, and space money supply, and we click OK. Okay, this is our VAR specification. Okay, let's look at an expanded view of it. Okay, this is a VAR specification. So we'll now go to the fourth step. Determine the maximum lag length criteria for the variables in the VAR using the Akaike information criterion and the squash criterion. Okay, we'll now go to our Eviews and let us determine the lag length criteria. Go to lag structure, go to lag length criteria. Let us include 12 lags for this. Okay, no. So let us include 10 lags for this. I'll be using 10, so let's include 10 lags for this. 10. Good. Now at 10 lags, the Akaike criterion and the squash criterion is at what? 9 lags. Okay, let us see an expanded view on our PowerPoint. Now this is it. AIC and the SIC indicate 9 lags. 9 lags. Now after we must have determined the lag order selection criteria, we now go to the next step. We now have to ensure that the VAR is well specified by checking for serial correlation in the residuals at appropriate lags. If need be, increase lags to solve autocorrelation problems. Now how do we do that? We have to go to our Eviews and go and make sure, we check, go to our residual tests, we go to autocorrelation LM test to check if at 9 lags there is no autocorrelation. Okay, we put in let's put in 15 this time. 15 lags to see. Okay, good. Now at the 9th lag, a null hypothesis is what's rejected, meaning that is not rejected, meaning there is no serial correlation because the probability value is greater than 0.05. Let's look at an expanded version of this. Now you see, checking for serial correlation, we discover that at that same 9 lags, we can report there is no serial correlation. We accept the null hypothesis of no serial correlation. Okay, now that we accepted that, let us check the next step. Let's check the next step. The next step is take the VAR model and include the maximum order of integration as additional lags of each of the variables into each equation. Take the VAR model and include the maximum order of integration as additional lags of each of the variables in into each equation. Now what do we mean by that? The maximum order of our study is 2. Maximum order of integration. And note, it is essential that you don't include the coefficient for the extra 2 lags when performing the WAT test. They are just there to fix up the asymptotics. Hence, leave the interval at the appropriate lag length devoid of autocorrelation. Our lag length is 9. Leave it at 1 to 9 like this. Okay, we'll now go to estimate. We leave it at 1 to 9. We change this to leave it at 9. Okay, let's go back to our lesson. 9. And then the extra 10 and 11th lag of each variable to be at the exogenous section. Okay, now go to exogenous section. Let's copy this. Okay, and put them at the exogenous section. Paste. Okay, the 10th and 11th lag. Let's put 11 lags. Okay, this one here too. 11 lags. Okay, then we click OK. Okay, now that we click, let's look at the presentation. Okay, now this is what we've seen. The maximum order of integration is what? Is 2 lags. Is 2. Then the position in which we know there is no serial correlation is 9 lags. We now put 1 and 9 here like I did initially. And then we have the total 11 lags. So we include a total number of 11 lags to our bar model, which we include here. And so once we've done that, we'll now check for the lag, the Toda-Yamamoto. That's what we'll do next. We'll look at this. Next step is to do what? Undertake the Toda and Yamamoto causality. After we've done. So now let us undertake the Toda and Yamamoto causality in our Eviews. We move to our lag structure. We go to Granger causality and we click Granger causality. Good. Now do we see? Do we see now? This is our result. Now let us see an expanded view of the result in on a PowerPoint. And this is what we got, exactly what we got in output. See the probability values are what are less than 0.05. When we look at this one, we can also accept it at 0.05 level. Now the null hypothesis that there is no causality is rejected. Why? Because money supply gradually causes GDP. Causality relationship is significant at the 5% level. Also, GDP gradually causes money supply. Causality relationship is significant at the 5% level. Now, what do we say? We now say that there is a significant bidirectional causality relationship between GDP and money supply. In other words, we can now say that what money supply significantly predicts GDP, and also GDP significantly predicts what money supply. So this is the Toda and Yamamoto causality procedures. You can also try that at your own leisure time. And when you do that, try to compare with Granger and see if you would also get a significant result. But what we've shown now is what the Toda and Yamamoto causality test. Thank you very much.